Imagine humanity 1 million years from now. We have conquered disease, colonized thousands of worlds, and harvested the energy of stars. To us, such a civilization would look like gods, and yet even this civilization may face a humiliating truth: they might never leave the Milky Way. No matter how intelligent they become, no matter how advanced their technology becomes, and no matter how long they survive, hidden within the laws of physics may be a barrier so enormous that even the most powerful civilization imaginable can never overcome it. Tonight, we're going to find that barrier. For most of human history, the future has looked like an endless series of horizons. Every time we reached one, another appeared beyond it. Ancient civilizations dreamed of crossing mountains. Later generations crossed oceans. The 20th century conquered the skies, and the 21st began reaching into space. The pattern seemed obvious. The impossible keeps becoming possible. Because of that pattern, many people assume humanity's cosmic future has already been written. First, we established settlements throughout the solar system. Then we spread to nearby stars. Eventually, we colonized the entire Milky Way, and after that, other galaxies. The logic feels natural, almost inevitable. If civilization survives long enough, why wouldn't it continue expanding forever? Why wouldn't a species capable of crossing interstellar space eventually cross intergalactic space as well? At first glance, there appears to be no reason. After all, a galaxy is simply a larger destination, a bigger journey, a more ambitious frontier. But hidden inside that assumption is a mistake so profound that it changes everything. Because the universe is not scaled the way our intuition thinks it is. Human beings evolved on a small world. Every experience in our lives takes place across distances that are tiny compared to the cosmos. Even the largest structures we encounter, oceans, continents, entire planets, are insignificant on astronomical scales. Our brains are remarkably powerful, but they were never designed to understand the universe. And nowhere is that failure more obvious than when we begin talking about galaxies. When people hear the word galaxy, they often imagine a collection of stars grouped together in space. Which is true, but it is also deeply misleading. The Milky Way is not simply a collection of stars. It is an empire of stars, a vast gravitational city containing hundreds of billions of suns, countless planets, immense clouds of gas and dust, ancient stellar graveyards, black holes, neutron stars, and structures so large that light itself requires tens of thousands of years to cross them. Everything humanity has ever known exists inside the single cosmic island. Every human being who has ever lived, every war, every kingdom, every scientific discovery, every dream, every religion, every work of art, every act of love, and every moment of suffering. All of it has occurred within an unimaginably small corner of one galaxy among trillions. And yet, despite its staggering size, the Milky Way is not the universe. Not even close. When powerful telescopes peer into the darkness beyond our galaxy, they reveal something extraordinary. The night sky is not mostly empty. It is crowded. Every faint smudge of light scattered across deep space images is often another galaxy. Each one contains its own stars, its own planets, and perhaps its own civilizations wondering whether they are alone. The observable universe contains more galaxies than our ancestors ever believed possible, an ocean of cosmic islands stretching beyond comprehension. And naturally, this inspires an irresistible dream. If we can reach one island, perhaps we can reach them all. It is one of the most optimistic ideas humanity has ever produced, a future in which intelligence expands endlessly across the cosmos, a future in which no destination remains forever out of reach, a future in which the universe gradually becomes humanity's home. But optimism is not evidence. And dreams are not physics. Because the moment scientists begin examining the actual distances involved, something strange happens. The dream begins to encounter resistance. Not political resistance, not economic resistance, not even technological resistance. Something far more fundamental. The structure of reality itself. This is where the story becomes uncomfortable. Most limitations throughout history have eventually disappeared. The limits of transportation disappeared. The limits of communication disappeared. The limits of computation continue to fall year after year. As a result, we have developed an almost instinctive belief that every problem is ultimately an engineering problem. Need more speed, build better engines. Need more power, build better reactors. Need greater intelligence, build better computers. The assumption hiding beneath modern civilization is simple. Given enough time, every barrier can be overcome. But physics does not promise that. In fact, modern physics repeatedly suggests the opposite. Some limits appear negotiable, others appear absolute, and the distinction between those two categories may determine the future of every civilization that has ever existed. Imagine discovering an intelligent species somewhere else in the Milky Way, a civilization thousands of years ahead of us, perhaps millions. Their technology would seem miraculous. They might manipulate matter at the atomic scale, construct artificial worlds, and harness the energy output of entire stars. To us, they would appear unstoppable. Yet the same laws of physics that govern our universe would govern theirs. The same speed limits, the same distances, the same constraints. No amount of intelligence changes the structure of reality. No amount of progress changes the size of the cosmos. And this leads to a disturbing possibility. What if every civilization eventually reaches the same conclusion? What if there comes a point where expansion stops, not because a civilization collapses? Not because it chooses to stop exploring, but because the universe itself imposes a boundary, a horizon beyond which even the most advanced technology cannot carry them. If such a boundary exists, it would transform our understanding of the future. The Milky Way would no longer be the first step toward the universe. It would become the largest arena civilization can ever occupy, a cosmic continent surrounded by an ocean too vast to cross. An island so enormous that life inside it could spend millions of years exploring its stars and never exhaust its possibilities, and yet still remain trapped. The word trapped sounds dramatic, perhaps even pessimistic. But consider the alternative. Maybe the true wonder is not that the universe has limits. Maybe the wonder is that creatures living on a tiny planet developed minds capable of imagining realities beyond those limits. After all, long before humanity built rockets, we dreamed of reaching the moon. Long before we understood galaxies, we imagined traveling among them. Our imagination has always outrun our capabilities. That is one of the defining characteristics of intelligence, the ability to envision destinations we may never reach. And nowhere is that more evident than in our dream of leaving the Milky Way. Because before we can determine whether that dream is achievable, we must confront a question that most people never seriously ask. How big is the challenge, really? How vast is the gulf separating galaxies? How large is the cosmic ocean surrounding us? And what happens when we stop relying on intuition and start looking at the numbers? Because the numbers are where the true story begins, and once we understand them, the possibility that we may never leave the Milky Way starts to feel far less like science fiction and far more like reality. The numbers are where the dream begins to change. Up to this point, leaving the Milky Way sounds like an engineering challenge. Build faster ships, develop better energy sources, give civilization enough time, and the problem eventually disappears. That is how most people instinctively think about the future. But the universe does not care about intuition. The universe cares about scale. And scale is where intergalactic travel becomes something far stranger than most people realize. Consider the Earth. For most of history, crossing from one side of the planet to the other seemed impossible. Oceans looked endless. Continents appeared unimaginably distant. Yet today, a passenger can fly around the world in less than 2 days. The lesson feels obvious. Distances shrink when technology improves. Now move outwards. The Earth circles the Sun at a distance of roughly 150 million kilometers. That number already exceeds ordinary human comprehension. If every kilometer were a single step, reaching the Sun would require a journey far longer than the entire history of civilization. Yet on cosmic scales, the distance between Earth and the Sun is practically nothing. Light, the fastest thing in the known universe, crosses that gap in just over 8 minutes. 8 minutes. That is the first hint that our everyday sense of distance is completely detached from reality. Next, consider the outer planets. Neptune orbits so far away that sunlight takes more than 4 hours to reach it. The solar system suddenly feels much larger than it did a moment ago. But even this immense system occupies only a tiny bubble within something vastly greater. The nearest star beyond our Sun is Proxima Centauri. The distance is not measured in millions of kilometers, or billions, or even trillions. Astronomers had to invent a different language entirely. Proxima Centauri is more than 4 light-years away. That means the light reaching Earth tonight left that star more than 4 years ago. If humanity launched one of its fastest spacecraft toward it, the journey would not take months. It would take tens of thousands of years. Already, the scale is becoming uncomfortable. The nearest star is not next door. It is separated from us by an abyss. And yet, compared to the size of the Milky Way, even that abyss is almost insignificant. Our galaxy stretches across roughly 100,000 light-years. Think about what that means. If a beam of light began its journey from one side of the Milky Way today, it would still be traveling 100,000 years from now. When that light finally reached the opposite side, every nation currently existing on Earth would be gone. Entire civilizations would have risen and fallen. Languages would have evolved beyond recognition. That is the scale of a single galaxy. Suddenly, colonizing the Milky Way no longer sounds easy. It sounds like a project measured not in centuries, but in geological ages. And yet the Milky Way is merely one galaxy among countless others. This is the point where most minds quietly surrender. The numbers become so large that they stop feeling meaningful. 1,000 feels larger than 100. 1,000,000 feels larger than 1,000. But eventually, the brain loses its ability to visualize the difference. Intergalactic space exploits that weakness. The nearest major galaxy to our own is Andromeda. When people first hear about Andromeda, they often imagine it sitting just beyond the edge of the Milky Way, waiting as the next destination on humanity's journey. Reality is less comforting. Andromeda is approximately 2.5 million light-years away, not 2,500, not 2.5 million kilometers. 2.5 million years, moving at the speed of light. The fastest speed nature appears to allow. To appreciate how extreme that is, imagine compressing the entire history of human civilization into a single year. Recorded history would occupy only a tiny fraction of that timeline. Now multiply that span hundreds of times. Only then do you begin approaching the travel time required for light itself to cross the gulf between the Milky Way and Andromeda. Andromeda is not a neighboring city. It is not a neighboring continent. It is not even a neighboring planet. It is a distant cosmic island separated from us by an ocean so vast that ordinary language becomes almost useless. Yet Andromeda is considered close. That is the shocking part. In cosmic terms, Andromeda is one of our nearest neighbors. Beyond it lie countless galaxies scattered across distances that climb into tens, hundreds, and thousands of millions of light years. The deeper astronomers look into space, the more galaxies they discover. Every direction reveals more islands in the darkness, more destinations, more horizons, more impossible distances. This creates a strange psychological illusion. When we see images of galaxies, they appear close together. They seem like pieces of a connected structure. Our brains interpret the picture the same way they interpret cities on a map. But the map is lying to us. The empty space between galaxies is the dominant feature of the universe. Stars occupy only a tiny fraction of a galaxy. Galaxies occupy only a tiny fraction of the cosmos. Most of reality is emptiness. Vast, cold, silent emptiness. And that emptiness is the obstacle. People often imagine space travel as a problem of reaching destinations. In truth, it is a problem of surviving distances. The destination is easy to identify. The distance is what destroys the dream. Because every increase in scale transforms the challenge. Crossing an ocean requires a ship. Crossing a continent requires infrastructure. Crossing a planet requires advanced transportation. Crossing interstellar space requires entirely new civilizations. Crossing intergalactic space may require something beyond civilization itself. And here we encounter a profound contradiction. Human imagination evolved without limits. Physics did not. Our minds can effortlessly picture a ship leaving the Milky Way and sailing toward another galaxy. The image feels natural. It feels achievable. But imagination pays no price for distance. Reality does. Reality charges for every kilometer, every second, every unit of energy, every gram of mass. The bill grows larger and larger until the numbers become almost absurd. This is why discussions about intergalactic travel often drift into fantasy. The scales involved are so extreme that they tempt us to ignore them, yet understanding those scales is essential. Because the distance between galaxies is not merely a large version of the distance between stars, it is a fundamentally different category of problem. A problem so enormous that it forces us to confront one of the most important discoveries in modern physics. The universe has a speed limit, and that speed limit changes everything. Because once we understand how fast anything can travel through reality, we can finally begin asking the question that matters most. Even if humanity becomes a civilization of unimaginable power, can anything ever move fast enough to cross the cosmic ocean? For a moment, set aside rockets, engines, and technology. Imagine possessing perfect determination. Imagine a civilization willing to devote 10,000 years, 100,000 years, even 1,000,000 years to a single voyage. Would patience solve the problem? At first, it seems like it should. Distance is only distance. Given enough time, any journey can be completed. But that assumption hides another trap. The universe is not simply large. It is governed by rules, and some of those rules are so deeply woven into reality that every particle, every star, every galaxy must obey them. A traveler cannot choose which laws apply, neither can a civilization. No matter how advanced humanity becomes, our future descendants will still inhabit the same universe. they will still move through the same spacetime. They will still confront the same fundamental restrictions discovered by physics. This is where the conversation begins to shift. The challenge is no longer about maps. It is no longer about measuring distances between galaxies. It becomes a question about reality itself. How fast can anything travel? Can technology continue accelerating forever? Or is there a point beyond which the universe refuses to cooperate? Because if a hard limit exists, then every dream of reaching another galaxy must pass through it first. And once we examine that limit, the true magnitude of the barrier surrounding the Milky Way finally comes into view. The next obstacle is not distance. It is speed itself. For thousands of years, humanity believed motion was simple. If you wanted to arrive somewhere faster, you simply moved faster. There seemed to be no fundamental limit, no cosmic rule preventing an object from accelerating indefinitely. The universe appeared open, boundless, free. Then in the early 20th century, a quiet revolution changed everything. It did not come from a giant machine or a spectacular discovery in the sky. It came from a young patent clerk who asked a deceptively simple question. What would the universe look like if you could ride alongside a beam of light? The answer would transform physics forever. Before Albert Einstein, scientists already knew something strange about light. No matter how observers moved, light always appeared to travel at the same speed. This was deeply unsettling because it violated common sense. Imagine standing beside a road and watching a car pass. If the car is traveling at 100 kilometers per hour and you begin running in the same direction, the car's speed relative to you decreases. This is how motion normally works. But light refuses to obey this intuition. No matter how fast you move, light still races away at exactly the same speed. It is as if reality itself adjusts to preserve that number. Einstein took this bizarre fact seriously. And what he discovered was astonishing. Space and time are not fixed. They are flexible, stretchable, interconnected. The universe bends them in order to protect a single cosmic speed limit. The speed of light. Because humanity's dream of becoming an intergalactic civilization depends on one assumption: that distance can eventually be conquered through speed. But what if speed itself has a ceiling? What if no amount of technological advancement can break through it? Imagine a civilization millions of years more advanced than ours. They possess technologies we cannot comprehend. They manipulate matter with precision beyond imagination. They command energies that dwarf entire planets. To us, they would seem almost supernatural. Yet relativity makes a remarkable prediction. No matter how advanced they become, they still cannot simply ignore the speed limit. The laws of physics do not care how intelligent a civilization is. They do not grant exceptions. Every species inhabits the same universe. Every civilization faces the same restrictions. And this leads to an unsettling possibility. Perhaps intergalactic travel is not difficult because our technology is primitive. Perhaps it is difficult because reality itself was never designed to make such journeys easy. The contrast is profound. Human imagination sees the cosmos as an open frontier. Physics sees it as a landscape filled with barriers. Human ambition asks, how far can we go? Reality responds, how fast can you move? And the answer may determine the fate of every intelligent species in existence. Of course, there is a fascinating twist hidden inside relativity. As objects approach the speed of light, time itself begins to behave differently. Clocks slow down, distances contract. The universe becomes increasingly strange. From the perspective of travelers moving near light speed, a journey that appears impossibly long to outside observers can feel dramatically shorter. This sounds like a loophole, a potential escape from the tyranny of distance. And in some ways, it is. A sufficiently advanced civilization might cross enormous stretches of space while experiencing far less time than the rest of the universe. For the travelers, the voyage could feel manageable. But this solution comes with a cost. The outside universe continues aging. Centuries pass, millennia pass, entire civilizations rise and disappear. The travelers arrive at their destination only to discover that the world they left behind has become ancient history. The distance problem changes form, but it does not disappear. Relativity offers remarkable possibilities, yet it refuses to offer miracles. And this is where many popular visions of the future begin to collide with reality. Science fiction often portrays the galaxy as a network of connected worlds. Characters travel freely between stars. Civilizations communicate across immense distances. The cosmos feels accessible. The real universe appears far less cooperative. Every journey must negotiate with relativity. Every ambition must confront the speed limit. Every dream of expansion must pass through the same narrow gate. The farther we look, the more significant that gate becomes. And there is another reason physicists take this problem so seriously. Even approaching light speed requires something extraordinary. Energy. Vast quantities of it. The speed limit is not merely a barrier because it restricts motion. It is a barrier because getting close to it becomes increasingly expensive. Each fraction of additional speed demands greater sacrifices, greater resources, greater technological capability. The closer a spacecraft moves toward light speed, the more energy it consumes. The numbers escalate rapidly, then violently, then almost beyond comprehension. This is where the challenge of leaving the Milky Way transforms yet again. The problem is no longer just distance. It is no longer just speed. It becomes a question of power. How much energy would it take to push a civilization toward the edge of what physics allows? Could humanity ever generate such power? Could any civilization? Or does another wall stand waiting beyond the speed limit? Because if relativity establishes how fast we can travel, energy determines whether we can even attempt the journey. And when we begin calculating those requirements, the situation becomes even more daunting. The universe may have imposed a speed limit, but the price of approaching that limit may be even more terrifying. Even if the speed of light sets a strict limit on how fast anything can move, there is a natural response that seems obvious at first glance. If speed is limited, then we simply need more energy, more power, more advanced engines, more civilization-scale engineering. Because throughout human history, energy has always been the key that unlocked new levels of progress. Fire extended human capability. Steam power reshaped civilization. Electricity transformed communication. Nuclear energy revealed a new layer of physical reality. So it feels reasonable to assume that intergalactic travel is just the next step in this pattern, a problem waiting for enough power to solve it. But when physicists begin calculating what enough power actually means on intergalactic scales, something unsettling happens. The numbers stop feeling like engineering problems and start feeling like astronomical impossibilities. To understand why, we need to begin with something simple. Motion at low speeds requires modest energy. A car, a plane, a rocket, all of these systems operate within energy ranges that human civilization can produce. But as you approach relativistic speeds, the rules begin to shift. Energy is no longer linear. It grows exponentially. Each step closer to the speed of light demands dramatically more energy than the previous one. At first, this seems manageable, then it becomes extreme, then it becomes overwhelming, and finally, it becomes unphysical for any object with mass to reach the limit at all. Now imagine scaling this requirement up to a spacecraft large enough to carry a civilization, not a probe, not a robotic mission, but a self-sustaining world, a generation ship capable of surviving thousands of years. The energy requirements immediately enter a regime that no human system can meaningfully approach. But even that is still only the beginning. Because intergalactic travel does not require reaching nearby stars. It requires crossing millions of light years. And that changes everything. To move something massive at a significant fraction of light speed across such distances would require energy on a scale that begins to overlap with stars themselves. Not metaphorically, literally. A single star converts millions of tons of mass into energy every second, and even that output may not be enough to accelerate a large vessel to the speeds needed for intergalactic travel in any reasonable timeframe. This is where theoretical propulsion concepts begin to appear: antimatter engines, fusion drives, beamed energy propulsion, stellar lifting, Dyson-level megastructures. Each idea pushes the boundaries of what we can imagine engineering. But each also reveals the same underlying truth. The universe is expensive. Every attempt to increase speed or scale requires exponentially more energy, and there is no indication that this curve ever flattens. Instead, it climbs relentlessly. Now consider what it would mean for a civilization to attempt something truly ambitious, not just reaching another star system, but reaching another galaxy. Even if we ignore relativistic constraints for a moment, the sheer energy required to push meaningful mass across intergalactic distances becomes staggering. We are no longer talking about planetary resources or stellar resources. We are talking about galactic resources. A civilization attempting intergalactic travel at scale would need to harness energy comparable to the output of entire stars over vast periods of time. And likely far more than that if they hope to do it efficiently. At this point, something strange becomes clear. The problem is no longer just about building better engines. It is about whether a civilization can even access enough energy in the first place. This leads to one of the most important ideas in modern astrophysics: the concept of civilization scale. We often measure technological progress in terms of tools, but on cosmic scales, what matters is not the sophistication of tools. It is the total energy a civilization can control. A Type I civilization controls planetary energy. A Type II civilization controls stellar energy. A Type III civilization, in theory, controls galactic energy. And only at that level does intergalactic ambition even begin to appear physically plausible. But even this classification hides a deeper problem, because controlling a galaxy does not mean escaping it. It means fully utilizing it. There is a critical difference between mastering a system and leaving it. A civilization may become powerful enough to harness the energy of billions of stars, but that does not guarantee the ability to project that power across millions of light years of empty space. The universe does not automatically convert capability into mobility, and intergalactic space is not just large, it is mostly empty, which makes it uniquely hostile to energy transfer. Beams disperse, signals weaken, matter becomes sparse, distances stretch into scales where even light itself struggles to preserve coherence over time. So even if a civilization achieved galactic-level energy control, another question emerges. How do you actually use that energy to move something across nothingness? Because the space between galaxies is not a highway. It is a a vast, expanding, low-density emptiness where almost nothing exists to push against, reflect from, or interact with. In everyday engineering, movement depends on interaction. Wheels push against the ground, wings push against the air, engines push against expelled mass. But in intergalactic space, there is almost nothing to push against. It is not just far away, it is structurally empty. This creates a subtle but devastating constraint. Energy alone is not enough. Energy must be coupled with something, a medium, a mechanism. A physical process capable of translating power into motion across a void. And the further we push outward, the fewer options remain. This is where intergalactic travel stops looking like a scaling problem and starts looking like a fundamental design problem of the universe itself. Because the same physics that allows stars to shine and galaxies to form also creates vast empty regions between them, as if the universe naturally clusters structure into islands surrounded by oceans of nothing. And those oceans are not just empty space. They are barriers defined by the absence of usable interaction. At this stage, even the most optimistic engineering proposals begin to feel strained, because every solution eventually runs into the same wall. More energy helps, but only up to a point. After that, the limiting factor is no longer power generation. It is how reality itself responds to motion through emptiness. And this is where the story begins to shift again. Because if energy is not the final answer, then perhaps something deeper is limiting us. Perhaps the obstacle is not just technological, not just physical, but structural, built into the architecture of spacetime itself. And to understand that, we must move beyond engines, beyond civilizations, and even beyond energy. We must enter the most extreme environment in the universe. The space between galaxies. Between galaxies lies a region that sounds almost peaceful when described in simple terms. Empty space, a void, nothingness. But that simplicity is deceptive, because in physics, nothing is never truly nothing. And when we examine intergalactic space closely, the picture becomes far more hostile than most people ever imagine. To understand why crossing it may be so difficult, we first need to erase a mental illusion. The illusion is this: that space is a calm, empty stage where objects simply travel freely once they are given enough speed. That is not how the universe works. Space is not empty in the way a room is empty. It is active, dynamic, filled with invisible processes, fields, and radiation that never stop moving, even in the darkest regions of the cosmos. And between galaxies, these effects combine into an environment that is not only empty, but unforgiving. Let us begin with something subtle but important. Even in intergalactic space, there is no true vacuum. There are still stray hydrogen atoms drifting at extremely low densities. There is still the cosmic microwave background radiation, the faint afterglow of the Big Bang, permeating every direction. There are also high-energy particles traveling at nearly the speed of light, remnants of distant supernovae and active galactic nuclei. Individually, these things seem harmless. A few atoms here, a few photons there, almost nothing. But the problem is not what exists in a single moment. The problem is what happens over time and at extreme speeds. Imagine a spacecraft traveling at a significant fraction of the speed of light. From its perspective, the universe ahead is not calm. It is a storm of incoming particles. Even a single hydrogen atom, insignificant under normal conditions, becomes dangerous when collided with at relativistic velocities. The energy of impact is no longer microscopic. It becomes comparable to high-energy particle collisions in human-built accelerators. Now multiply that by trillions of impacts over the course of a journey. What seems empty becomes a constant bombardment, a slow erosion of structure, a persistent attempt by the universe to break apart anything trying to cross it. But radiation is only the beginning. The cosmic microwave background fills all of space with low-energy photons, individually harmless, yes, but at high velocities, these photons become increasingly energetic in the reference frame of a fast-moving object. What was once invisible heat becomes a growing field of radiation pressure and particle interaction. The faster you go, the more intense the universe becomes. This leads to a strange and counterintuitive reality. Speed does not simply reduce travel time. Speed changes the nature of space itself. Intergalactic travel is not just movement through distance. It is exposure to a transforming environment. But even this is still not the greatest challenge, because intergalactic space introduces something even more fundamental. Isolation. On Earth, survival depends on constant interaction with an environment rich in energy and matter. Atmosphere provides pressure, oceans provide chemistry, gravity provides structure. In space, especially between galaxies, almost all of those supportive conditions disappear. There is no air, no accessible material, no nearby energy sources, no easy way to repair, refuel, or stabilize a system that begins to fail. A spacecraft traveling between galaxies must carry everything it needs from the very beginning, every atom, every joule of energy, every replacement component, everything. And that immediately introduces a brutal constraint. The larger and more ambitious the mission, the more massive it becomes. The more massive it becomes, the more energy it requires to accelerate, and the more energy required, the harder it becomes to leave in the first place. This is a recursive trap built into the structure of physics. But let us go deeper. Even if we solve propulsion, even if we solve energy, even if we solve shielding against radiation and particle impacts, there remains another problem that cannot be ignored. Time. Intergalactic distances are so extreme that even near light-speed travel takes millions of years in external reference frames. This means that any civilization attempting such a journey must confront the reality that it is not simply traveling through space. It is traveling through history. Civilizations evolve, stars age, galaxies change shape, entire regions of the universe transform over the course of 1,000,000 years. A mission launched with perfect planning may arrive in a universe that no longer resembles the one it left behind. This creates a profound disconnect. A signal sent from one galaxy may arrive in another at a time when both the sender and the receiver have changed beyond recognition. Civilizations evolve, technologies advance, contexts shift. What was transmitted as a coherent message may arrive as something outdated, disconnected, or even meaningless. So even in a universe of information, distance still matters. Perhaps the most important limitation is more fundamental. Information transfer still requires a medium. Light, electromagnetic waves, quantum processes. Something must carry the signal, and that means information is still bound by the same speed limit that governs physical matter. Relativity does not disappear simply because the payload is no longer a spaceship. It still governs causality itself. So the question becomes sharper. If both bodies and minds are constrained by the same cosmic speed limit, then is there any meaningful way to achieve true intergalactic presence? Or is every form of expansion ultimately slowed by the same underlying rule? At this point, some thinkers propose an even more radical idea. Perhaps consciousness does not need to travel or be transmitted at all. Perhaps it can be locally instantiated wherever conditions allow. In this view, intelligence is not something that moves through the universe. It is something that emerges within it, like a pattern that appears wherever complexity reaches a certain threshold. If that is true, then intergalactic expansion is not a journey. It is a process of replication. Civilizations do not travel to new galaxies. They recreate themselves there, but this raises another uncomfortable implication. If intelligence can spontaneously emerge wherever conditions permit, then there is no guarantee that what emerges is connected to what came before. Each instance may be independent. Each civilization may be isolated. Each conscious structure may be fundamentally alone. Which brings us back to a haunting possibility. Even in a universe filled with intelligence, communication across galaxies may still be fundamentally limited, not because intelligence does not exist, but because connection itself is constrained. And now the problem comes full circle. We began by asking whether humanity could physically leave the Milky Way. Then we explored whether energy or speed could make it possible. Then we considered whether information or consciousness could bypass those limits. But each layer reveals the same underlying truth. The universe enforces boundaries not only on matter, but on interaction itself, on how fast anything can influence anything else, on how far cause and effect can propagate. And if that is true, then intergalactic travel is not just a problem of engineering or identity. It is a problem of causality. The structure of reality itself determines what can ever be connected. And if galaxies lie beyond the practical reach of causal connection, then leaving the Milky Way is not simply difficult. It may be fundamentally outside the domain of what a single civilization can ever fully experience as a unified whole. This leads to a deeper shift in perspective. Maybe the question was never, how do we leave the Milky Way? Maybe the real question is, what does it mean to exist inside a universe where leaving certain regions is physically possible, but causally unreachable? And once that question is asked, the story stops being about engines or minds and starts becoming about the nature of reality itself. If physics, energy, and even information are all constrained by the same cosmic limits, then the problem of leaving the Milky Way begins to take on a more unsettling shape. It stops being a question of technology. It stops being a question of intelligence, and slowly becomes a question of identity itself. Because there is a hidden assumption behind everything we have discussed so far. We assume that we are something that can move. Something that can travel. Something that can be transmitted, replicated, or carried across space. But what if that assumption is wrong? What if the deeper truth is that consciousness is not a thing that moves through the universe, but something that only exists under very specific conditions? This is where physics collides with philosophy in a way that becomes almost impossible to separate. Because once we start talking about copying minds, transmitting information, or reconstructing consciousness elsewhere, we are forced to confront a question that has no clean answer. What does it actually mean to remain the same person over time? At first, the answer seems obvious. You are the same person today that you were yesterday because there is continuity. Your body persists, your memories connect, your experiences flow into each other without interruption. But even this simple idea begins to break down under closer inspection. Every cell in your body is replaced over time. Your thoughts are constantly changing. Your memories are not perfect recordings, but reconstructed interpretations. And yet, despite all of this change, you still feel like a continuous self. So identity cannot simply be physical matter, nor can it be a fixed snapshot of information. It must be something more subtle, a pattern that persists through change. Now imagine that pattern being interrupted, or copied, or transmitted. If a perfect copy of your mind were created somewhere else in the universe, complete with your memories, personality, and sense of self, what would that copy be? Would it be you, or something that only believes it is you? This question is not just philosophical speculation. It becomes central when we imagine intergalactic expansion through information or digital consciousness. Because the moment we replace travel with copying, we must confront the fact that there is no longer a single continuous observer moving through space. Instead, there are branches, divergences, multiple instantiations of the same original pattern, and each one begins to develop independently from the moment of creation. From a distance, this may still look like expansion. A civilization spreading across galaxies like a growing network of minds, but inside that system, something important is lost. Unity. The sense that there is a single us experiencing the journey. Instead, there are many versions of us, each isolated within its own causal bubble. This introduces a paradox. If civilization expands by replication rather than travel, then what exactly is being preserved? Is it continuity of identity, or just continuity of structure? And if structure alone is preserved, does that count as survival, or only imitation? To explore this further, consider a more grounded analogy. Imagine a book being copied across time. Each copy contains the same words, the same story, the same structure, but each copy exists independently. Destroying one copy does not destroy the others, and none of them are aware of each other's experiences. Now replace the book with a mind. The implications become uncomfortable very quickly. Because the idea of you begins to fragment into multiple versions that share a common origin, but no longer share a unified experience. At this point, intergalactic travel through information stops being a story of exploration. It becomes a story of divergence. But even this assumes that such copying is possible in the first place, and physics introduces another complication. Information is not abstract in the universe. It is physical. It must be encoded in matter or energy. It must obey thermodynamics. It must exist within spacetime. Which means that even a perfect digital mind is still bound by the same constraints as any other physical system. It requires energy. It requires storage. It requires stability against noise and decay. And most importantly, it requires a medium through which it can be transmitted, which immediately brings us back to the speed of light. Even if consciousness could be reduced to information, that information still cannot escape causality. It still cannot outrun the structure of spacetime. So even in a universe of digital minds, intergalactic separation remains a powerful divider. Two civilizations separated by millions of light years are not just far apart. They are causally disconnected for enormous periods of time. Their experiences cannot synchronize. Their decisions cannot influence each other in real time. Their evolution proceeds independently. This leads to a profound realization. Even if intergalactic expansion is technically possible in some form, it may not produce a unified civilization. Instead, it may produce isolated islands of intelligence drifting apart across cosmic history. Each galaxy becomes its own evolutionary experiment, its own timeline, its own interpretation of intelligence. From this perspective, the Milky Way is not just a location. It is a causal region, a bubble of shared influence, a domain within which information can circulate and remain coherent. Beyond it, coherence begins to break down, not instantly, but inevitably. And this changes the meaning of leaving entirely. Because leaving a region that you can never meaningfully interact with again is not the same as expansion. It is separation. Now consider what this implies for humanity's future. If we eventually spread across the Milky Way, even that achievement may already push us to the edge of our causal neighborhood. Communication between distant regions of our own galaxy could take tens of thousands of years. Coordination could become impossible. Shared identity could begin to fragment even within a single galaxy. And if that is true, then leaving the Milky Way is not the beginning of cosmic civilization. It may be the point where civilization itself stops being a unified concept. There is another layer to this problem that is even more subtle. Human beings experience time as a continuous flow. But physics does not require that flow to be synchronized across space. Relativity already tells us that time is not universal. Different observers experience different rates of time depending on motion and gravity. Now extend that across galactic distances. Even small relativistic effects accumulate over millions of years. Two regions of the galaxy can drift out of temporal alignment without ever physically moving far apart. Now imagine extending that to intergalactic scales. The result is not just spatial separation, it is temporal fragmentation. Different parts of a civilization may literally exist in different eras of reality. Some regions may be millions of years ahead, others may lag behind. There is no shared present, only overlapping histories. This creates a strange implication. A galaxy-spanning civilization would not experience itself as a single moment in time. It would experience itself as a layered structure of overlapping civilizations, each slightly out of sync with the others. And beyond the galaxy, that synchronization collapses entirely. At that point, the concept of civilization begins to lose meaning, because civilization requires communication, coordination, shared understanding, but those depend on causal connectivity, and causal connectivity weakens with distance until it eventually disappears. So when we ask whether humanity will ever leave the Milky Way, we are not just asking about propulsion or energy. We are asking whether identity, communication, and coherence can survive beyond a certain scale of spacetime. And physics suggests that they may not. Which brings us to a difficult conclusion. The universe may not forbid expansion, but it may forbid unity at large scales. You can spread, you can replicate, you can influence distant regions over time, but you may never remain a single coherent entity across the cosmos. And if that is true, then the Milky Way is not a prison in the traditional sense. It is a boundary of coherence, a region where cause and effect remain meaningfully connected, a place where we still mean something unified. Beyond it, that unity dissolves, slowly, quietly, irreversibly. And that changes the entire narrative of intergalactic travel, because the question is no longer whether we can leave. The question becomes what we lose when we do. And whether a civilization that spreads too far eventually stops being one civilization at all. Which leads to a final unsettling thought. Perhaps the universe does not prevent us from reaching other galaxies. Perhaps it simply ensures that whatever reaches them is no longer the same us that began the journey. Once identity, energy, and causality begin to collapse under intergalactic scales, a new possibility starts to emerge. If the universe is so hostile to conventional travel, then perhaps the problem is not that we are using the wrong technology. Perhaps we are using the wrong model of reality. Because hidden inside modern physics are a few ideas that seem to whisper something very different from everything we have discussed so far. Ideas that suggest spacetime itself may not be as rigid as it appears, and if spacetime can be bent, folded, or reshaped in extreme ways, then the question of leaving the Milky Way suddenly takes on an entirely new dimension. Instead of asking how to cross vast distances, we begin asking something more radical. Can distance be bypassed? At first, this sounds like pure speculation, but the mathematics of general relativity allows solutions that are far stranger than everyday intuition would suggest. One of the most famous of these is the concept of a wormhole, a hypothetical tunnel connecting two distant points in spacetime. On paper, a wormhole does something extraordinary. It does not require traveling through space. It connects two locations directly. As if the universe could be folded so that distant regions touch. If such a structure could exist and remain stable, it would transform intergalactic travel completely. A civilization would no longer need to cross millions of light years. They would simply step from one end of spacetime to another. Distance would become irrelevant. But there is a problem. Every known description of wormholes requires conditions that are far beyond anything we know how to create or sustain. They appear to collapse instantly unless held open by forms of matter or energy that remain purely theoretical. In many models, this includes something called exotic matter, which would need to possess negative energy density, a concept that has no confirmed large-scale existence in nature. So while wormholes are mathematically allowed, they remain physically uncertain. They sit at the boundary between what physics permits and what physics tolerates only in theory. Another idea emerges from a different corner of relativity, the concept of a warp drive. Instead of moving through space, a warp drive would manipulate space itself, contracting spacetime in front of a vessel, expanding it behind. The result would be a bubble of distorted spacetime that carries the ship forward without locally breaking the speed of light. From the outside, it might appear as though the ship is moving faster than light, but locally, it would still obey relativity. This idea sounds almost elegant. It preserves the rules of physics while bending the structure around them. However, once again, the engineering requirements are extreme. Early calculations suggest that stabilizing such a spacetime bubble would require energy comparable to planetary or even stellar scales. Later refinements reduced these estimates in theory, but the fundamental challenges remain unresolved. There is still no evidence that spacetime can be shaped in this way on macroscopic scales, and even if it could be, we return to the same recurring problem: stability, control, and energy. But these concepts share something important. They all attempt to solve the same underlying issue. Distance is too large, so instead of moving through it, they try to eliminate it. This is where speculative physics becomes particularly interesting. Because once you accept that spacetime might be manipulated, other possibilities begin to appear. Extra dimensions, quantum entanglement effects, vacuum energy manipulation. Each idea suggests different ways reality might be more flexible than it appears, but each also sits far beyond experimental confirmation. At the moment, they exist more as mathematical curiosities than engineering blueprints. Yet their existence in theoretical physics is important because it reveals something subtle about how we understand the universe. Physics does not only describe what is possible, it also maps the edges of what is imaginable within mathematical consistency, and those edges are far wider than our current technology. Still, even if one of these ideas turned out to be real, it would not automatically solve the problem of leaving the Milky Way. Because every shortcut introduces its own constraints. Wormholes, if they exist, may require pre-existing connections between distant regions of spacetime. Warp drives, if possible, may demand energy conditions that are effectively unreachable. And extra-dimensional travel, if it exists, may be limited by unknown geometric or quantum rules. In other words, every proposed shortcut replaces one barrier with another, but there is a deeper pattern emerging here. Every time physics offers a way to bypass distance, it also introduces a cost that grows with scale. It is as if the universe allows loopholes only in principle, not in practice. This raises an uncomfortable question. Are these ideas glimpses of future engineering possibilities, or are they simply reflections of the mathematical flexibility of our theories without physical realization in reality? We do not yet know. But there is another layer to this discussion that is often overlooked. Even if spacetime manipulation were possible, it does not solve the problem of causality, because any shortcut that connects distant regions instantly or near-instantly risks breaking the structure of cause and effect. Physics is built not only on energy and motion, but on consistency. If information can arrive before it is sent, or travel without respecting temporal order, the entire framework of predictability begins to collapse. This is why many solutions in theoretical physics are carefully constrained. The universe appears to resist not just faster than light travel, but anything that would destabilize causality itself. So even the most exotic ideas must respect a deeper rule: cause must precede effect. This brings us back to a central tension. We are searching for ways to leave the Milky Way, but every attempt to bypass distance collides with deeper structures of reality that seem designed to preserve consistency across spacetime. And consistency requires limits, which leads to a subtle realization. The universe may not be built to maximize accessibility. It may be built to preserve structure, to maintain order, to ensure that events remain connected in a coherent way. From this perspective, the difficulty of intergalactic travel is not an accident. It is a consequence of how reality maintains itself. But there is still one more idea worth exploring, a concept that sits at the intersection of physics, philosophy, and information theory. Instead of asking how to move through spacetime or around it, we ask whether movement is even the right concept at all. Because at the deepest level, modern physics suggests that reality is not composed of objects moving through space in a classical sense. It is composed of fields, probabilities, interactions, and information exchanges. In that framework, travel becomes less fundamental. What matters is not motion from point A to point B. What matters is correlation, interaction, connectivity. And when we look at intergalactic space through that lens, something becomes clear. The problem is not just distance. It is the weakening of correlation across distance. As separation increases, interaction probability decreases, signals weaken, forces diminish, causal influence fades. Eventually, regions of spacetime become effectively independent, not because they cease to exist, but because they no longer meaningfully affect each other within observable timescales. So even if a wormhole or warp drive were possible, the deeper issue remains. How do you preserve meaningful interaction across scales where the universe itself naturally suppresses connection? This is why many physicists and philosophers suspect that there may be a fundamental limit to coherent systems in the universe. Not a limit on existence, but a limit on unity, on how large a single integrated structure can become before it fragments into independent parts. And if that is true, then intergalactic travel is not just an engineering challenge. It is a boundary condition of reality, a point where coherence begins to dissolve. Which brings us back to the central question of this entire journey. If leaving the Milky Way requires breaking or bypassing so many layers of physical law, then why does the universe allow us to imagine it so easily? Why does our mind so naturally picture crossing galaxies if the structure of reality resists it so strongly? Perhaps that is the final clue. Maybe imagination is not a map of what is possible, but a reflection of what lies at the edges of possibility. And as we move forward, the question shifts one final time. If physics allows no clean escape, and identity itself fractures across distance, then what does it actually mean for a civilization to exist beyond its galaxy? And is there any version of us that could truly make that journey intact? If all previous barriers, energy, speed, identity, and spacetime geometry, begin to converge into a single pattern of resistance, then there is still one force in the universe that quietly changes the entire equation. A force that does not depend on technology, does not depend on intelligence, and does not depend on intention, the expansion of the universe itself. At first, this idea feels almost irrelevant to everyday thinking about space travel. We imagine space as a static backdrop, an empty stage where galaxies sit like fixed objects separated by large distances. But that image is incorrect. Space is not fixed. It is stretching, everywhere, all the time, and not in the way objects move away from each other through space, but in the deeper sense that space itself is expanding between everything. This was one of the most shocking discoveries in modern cosmology. When astronomers observed distant galaxies, they noticed something unexpected. Nearly all of them were moving away from us. More importantly, the farther away a galaxy was, the faster it appeared to recede. This was not because we were at a special location in space. It was because the universe itself was expanding uniformly. Like dots on a balloon being inflated, galaxies are not traveling across space in the traditional sense. Instead, the space between them is increasing. This subtle distinction changes everything, because if space itself is expanding, then distance is not a fixed quantity. It is dynamic, it grows over time, which means that the universe is not just large, it is becoming larger. And that has profound consequences for intergalactic travel. To understand why, we need to introduce a concept known as the cosmic horizon. This is not a physical wall. It is not an object. It is a boundary defined by the limits of expansion and the speed of light. Beyond a certain distance, galaxies are receding from us faster than light can travel toward them. Not because anything locally exceeds the speed of light, but because space itself is expanding faster than light can bridge the gap. This creates a strange and unsettling situation. There are regions of the universe that are already becoming unreachable, not in the future, but effectively right now in cosmic terms. Even if we sent a signal today, even if we traveled at the maximum possible speed allowed by physics, there are galaxies that we will never reach, ever, not because we are too weak, but because the universe is stretching faster than connection can occur. This introduces a new layer of separation beyond distance, a separation enforced by expansion, and this expansion is accelerating, driven by a mysterious component of the universe we call dark energy. We do not fully understand what dark energy is. We know it exists because we observe its effects. We see galaxies accelerating away from each other over time. We see the large-scale structure of the cosmos changing in a way that suggests something is pushing space outward, but its nature remains one of the greatest mysteries in physics. And yet its consequences are already clear. The universe is not only expanding, it is accelerating in its expansion. This means that the cosmic horizon is not fixed. It is moving inward relative to the structure of galaxies. More and more regions of space are crossing the threshold where they become causally disconnected. From a certain perspective, the universe is slowly isolating itself, not violently, not suddenly, but gradually, quietly, inevitably. Now consider what this means for the dream of leaving the Milky Way. Even if we ignore propulsion limits, even if we assume perfect engineering, even if we assume civilizations capable of near-light-speed travel or space-time manipulation, there is still a fundamental time constraint, a window of opportunity. Because galaxies are not static targets waiting to be reached, they are moving away, and in some cases, moving beyond reach. This transforms intergalactic travel from a spatial problem into a temporal one. It is no longer just about how far we can go. It is about how long the universe allows us to try. At present, galaxies like Andromeda are still gravitationally bound to the Milky Way. In fact, Andromeda is moving toward us, and in the distant future, the two galaxies will collide and merge into a single larger structure. But beyond our local group, the story changes. Distant galaxies are not bound to us. They are being carried away by expansion, which means that over time, fewer and fewer destinations remain reachable. The universe is not evenly accessible. It is stratifying into regions of different connectivity. Local clusters remain connected. Distant structures drift away. Eventually, vast portions of the cosmos become permanently isolated from each other. This leads to a remarkable implication. The future universe will not be a single unified expanse of galaxies. It will be a collection of separated islands of matter, each trapped within its own expanding region of space, each island effectively alone. Each cluster evolving independently, each region cut off from meaningful interaction with others. And this is not science fiction. It is a direct consequence of observed cosmic expansion. Now step back and consider the philosophical impact of this. For most of human history, the universe was assumed to be infinite in both space and possibility, a boundless arena where exploration could continue indefinitely. But modern cosmology suggests something very different. Not only is the universe structured, it is dynamically structured. Its accessible regions change over time, and those changes impose limits on exploration that are not technological, but temporal. This means that even if intergalactic travel were physically possible, it would still depend on timing. There are eras in cosmic history where expansion is possible, and there are future eras where it becomes impossible because the destinations themselves disappear beyond the horizon of causality. This introduces a quiet urgency to the story of civilization, not the urgency of human lifetimes, but the urgency of cosmic opportunity. There is a window in which the universe is still connected enough to allow movement between its largest structures, and that window may already be closing, slowly, imperceptibly, but consistently. Now return to the Milky Way. From our perspective, it appears as a vast island of stars, but from a cosmological perspective, it is part of a local gravitational system that is still coherent, still connected, and still capable of internal interaction. This local group of galaxies is an exception in a universe that is otherwise becoming increasingly disconnected, which leads to a profound realization. The Milky Way is not just our home. It is part of one of the last regions of large-scale cosmic coherence that will ever exist. Beyond it lies a universe that is not just distant, but dissolving in terms of connectivity. So when we ask whether humanity will ever leave the Milky Way, we are not only asking about engineering limits. We are asking whether we will ever move beyond the last stable island of cosmic interaction. Because once expansion fully dominates, leaving becomes less about capability and more about whether the destination still participates in the same causal structure. And if it does not, then it is no longer a reachable place in any meaningful sense. It is simply a mathematical location, a coordinate without interaction. This reframes everything. The universe is not a static collection of galaxies waiting to be explored. It is an evolving structure that determines what can remain connected over time. And intergalactic travel exists only within the narrow regions where that connection still survives. Which brings us back to the core theme of this entire journey. Every attempt to escape the Milky Way, through energy, speed, identity, space-time manipulation, or information, ultimately collides with a deeper constraint. Not the impossibility of movement, but the fragility of connection. And as we move forward, the final question emerges naturally. If the universe is gradually isolating its own structures, then what does it mean for intelligence to exist inside it? Is civilization destined to spread and fragment, or is there a deeper principle that defines where and how consciousness can meaningfully persist? Because the Milky Way may not just be a region of space. It may be one of the last places where the universe still allows things to remain connected. If the universe is actively separating itself into isolated regions, then a disturbing implication follows naturally. Even intelligence, no matter how advanced, may never fully escape its local island of reality. And if that is true, then a question that has haunted scientists for decades becomes even more unsettling. Where is everyone else? Because once you understand the scale of the Milky Way and the scale of the observable universe, the expectation of cosmic civilization seems almost inevitable. There are hundreds of billions of stars in our galaxy alone. Many of those stars have planets, and many of those planets exist in conditions that could, in principle, support life. And beyond our galaxy, there are billions upon billions of similar systems. Statistically, it seems almost unreasonable to think that intelligence has only emerged here. Which leads to one of the most famous questions in science. If intelligent life is common, then where are all the civilizations? Why is the sky silent? Why do we not see evidence of galaxy-spanning societies? And why is the universe not visibly structured by intelligence? This is the heart of what is known as the Fermi paradox. A simple question with a deeply uncomfortable implication. The more likely intelligence seems, the more strange its absence becomes. Now, over the years, many explanations have been proposed. Some suggest that intelligent life is extremely rare, or that civilizations inevitably destroy themselves before reaching advanced stages. Some propose that interstellar travel is too difficult, even for advanced species, while others suggest that we are being observed, but not contacted. Each explanation attempts to resolve the contradiction between expectation and observation. But if we place everything we have discussed so far into this framework, a new possibility emerges, one that does not require rare life, self-destruction, or deliberate silence. A possibility rooted instead in physics itself. What if civilizations exist, but are fundamentally constrained by the structure of the universe? What if the absence of visible galaxy-spanning empires is not evidence of rarity or failure, but evidence of limitation? To explore this, we return to a key idea. Intergalactic space is not just large, it is causally disconnected. We have already seen that beyond certain distances, galaxies recede faster than light can bridge the gap due to cosmic expansion. We have also seen that even within static space, relativistic constraints make travel across millions of light years effectively impossible on meaningful timescales. And we have seen that energy requirements, radiation hazards, and identity problems compound the difficulty further. Now combine all of these constraints. What emerges is not a single barrier, but a system of layered limits that operate at every level of reality. Distance limits physical travel, speed limits motion, energy limits capability, expansion limits reachability, causality limits interaction. Together, they form a structure that naturally divides the universe into regions of coherence and isolation. And if that structure is fundamental, then every civilization in the universe faces the same boundary conditions, not because they are similar to us, but because they exist in the same space-time. This leads to a striking reinterpretation of the Fermi paradox. Perhaps the universe is not empty of intelligence. Perhaps it is full of intelligence, but intelligence is distributed in isolated pockets that cannot meaningfully interact across cosmic distances. Each galaxy, or even each cluster of galaxies, may represent a separate arena of evolution, a separate experiment in complexity, a separate unfolding of intelligence that never fully connects with others. From this perspective, the silence of the universe is not surprising. It is expected, because silence is what happens when interaction becomes impossible. Now consider what this means for the idea of intergalactic civilizations. We often imagine civilizations expanding outward in waves, colonizing star systems, and eventually spreading across galaxies like ripples in water. But this image assumes continuous connectivity. It assumes that communication, travel, and coordination remain possible at large scales. If that assumption fails, the entire model collapses. A civilization cannot behave as a unified entity if its parts are separated by millions of years of communication delay. At that point, expansion does not produce a single civilization, it produces fragmentation. Independent branches of intelligence evolving separately, each unaware of the other's current state, and each developing its own trajectory. Over time, those branches may diverge so far that they are no longer meaningfully related. This introduces a deeper interpretation of the Fermi paradox. Maybe we do not see galaxy-spanning civilizations, because galaxy-spanning civilizations cannot remain civilizations in any coherent sense. They dissolve into distributed, unconnected systems long before they become visible as unified structures. So even if intelligence is common, its signature may be inherently local, confined, and fragmented. Now step back and reconsider the Milky Way in this context. Our galaxy is not just a collection of stars. It is a gravitationally bound system, a region where interactions are still possible across vast distances, even if delayed. A structure where information can still, in principle, circulate within a finite cosmic timescale. This makes the Milky Way fundamentally different from the expanding regions beyond our local group. The Milky Way is a coherent island in a universe that is increasingly incoherent at larger scales. And this coherence may be absolutely essential for what we recognize as civilization. Because civilization is not just technology, it is coordination, shared understanding, and the ability to act as a single system across space and time. Once that breaks down, civilization becomes something else entirely, not unified intelligence, but distributed intelligence. Now return to the question of leaving the Milky Way. If a civilization were to expand beyond this coherent region, what would actually happen? The first phase would likely be expansion into nearby star systems, which would still preserve some level of connectivity. But as distances increase, communication delays would grow, coordination would slow, and eventually, decision-making would fragment across regions that can no longer synchronize. At that point, the civilization is no longer acting as a single entity. It becomes a network of semi-independent systems. And if expansion continues further, even that network begins to dissolve. Beyond the galaxy, coherence may collapse entirely, which leads to a paradoxical conclusion. The more a civilization expands, the less it remains a unified civilization. Expansion does not necessarily equal growth in the traditional sense. It may simply equal dilution. Consider another implication. If advanced civilizations are aware of these constraints, they may deliberately choose not to expand beyond a certain scale, not because they lack the capability, but because expansion beyond coherence offers no meaningful benefit. There is no advantage in becoming a scattered intelligence that cannot coordinate, communicate, or share experiences within any practical timescale. From this perspective, the Milky Way is not a limitation. It is an optimal domain for sustained civilization, large enough to contain immense diversity, yet small enough to maintain causal connectivity and allow long-term coherence. Beyond it lies a universe that may be physically accessible, but functionally unusable for unified intelligence. This reframes the Fermi paradox yet again. Perhaps advanced civilizations are not absent, perhaps they are present, but they are not expanding outward in the ways we expect. The very concept of outward expansion may be fundamentally incompatible with maintaining what we define as civilization. Now, the silence of the cosmos takes on an entirely different meaning. It is not the silence of emptiness. It is the silence of separation, of systems too far apart to ever meaningfully interact, of intelligence confined within isolated islands of coherence scattered across an expanding universe. And if that is the case, then the Milky Way is not just our galaxy. It is our local domain of possible connection, our maximum arena of shared existence. Beyond it lies not a universe waiting to be explored, but a universe already drifting beyond the reach of unified understanding. Which leads to the most unsettling interpretation of all. The universe may not be hiding civilizations. It may be actively preventing them from ever becoming visible to each other at large scales. The question is no longer why we do not see them, but whether it is even physically possible for us to ever see them at all. If the universe naturally fragments intelligence into isolated pockets, then something subtle begins to shift in how we interpret existence itself. Throughout this entire discussion, the focus has been on travel, how to cross distance, overcome energy barriers, bypass space-time limits, and preserve identity across cosmic scales. But slowly, almost without noticing, the question stops being about movement and starts being about meaning. There is a deeper assumption hiding underneath every technological dream humanity has ever had, the assumption that the purpose of intelligence is expansion. We assume that the natural destiny of a thinking species is to spread outward indefinitely, to grow, to colonize, and to reach further into the universe until nothing remains unknown. But what if that assumption is not just incomplete? What if it is fundamentally wrong? To understand why this question matters, we need to step back from physics for a moment and look at something more basic: human history. Every major leap in civilization has been associated with expansion. We expanded across continents, across oceans, across scientific understanding, and across technological capability. It feels natural to project that same pattern into the future and assume it continues indefinitely into the stars. But every form of expansion in history has eventually encountered limits. Not always physical limits, but cognitive limits, organizational limits, and limits of coherence. There is a profound difference between growth and stability, between scale and unity, and between complexity and control. When we apply this distinction to a cosmic civilization, something interesting happens. The idea of leaving the Milky Way suddenly stops looking like an obvious next step and starts looking like a threshold beyond which coherence begins to collapse entirely. We have already seen hints of this in physics. Communication delays grow with distance, relativity prevents instantaneous coordination, cosmic expansion actively isolates regions of space, and identity becomes fragmented when continuity is broken. So the question becomes unavoidable. If expansion reduces unity, then what exactly are we trying to achieve? There are two possible interpretations of civilization's trajectory. In the first, intelligence is a force that spreads outward indefinitely, converting the universe into a structured network of controlled systems. In the second, intelligence is a localized phenomenon that emerges within bounded regions of spacetime, reaches a peak of complexity, and then stabilizes rather than expands. These two visions of the future are radically different. One assumes infinite reach, the other assumes finite coherence. Once you include relativity, expansion, and causality, infinite reach becomes increasingly expensive in every sense of the word. Energy, time, coordination, and information, everything becomes exponentially more difficult as scale increases. This leads to a profound possibility. Maybe intelligence does not naturally want to expand forever. Maybe expansion is just a developmental phase, not the final form of civilization. Imagine a civilization that has reached its maximum coherent size. It controls an entire galaxy, has access to vast energy resources, and has solved most material limitations. At this stage, further expansion into intergalactic space is technically possible in theory, but practically meaningless in terms of coordination. When communication delays stretch into hundreds of thousands or millions of years, shared decision-making becomes impossible, and even shared identity becomes ambiguous. At that point, what does expansion actually mean? If parts of your civilization cannot meaningfully communicate with other parts, are they still part of the same civilization, or are they independent descendants of a once unified system? This is where the concept of civilization itself begins to dissolve under scale. Civilization is not defined by size, it is defined by coherence, and coherence depends on interaction. If interaction breaks down, civilization breaks down with it, not into extinction, but into fragmentation. This suggests a surprising reinterpretation of cosmic history. Perhaps civilizations do not expand until they fill the universe. Perhaps they expand until they lose unity, and then they stabilize within the largest region where unity is still possible. In our case, that region is the Milky Way. What if the Milky Way is not a prison, but a natural boundary of coherent intelligence? It is a region large enough to contain unimaginable complexity, but small enough to preserve causal connection, a scale where intelligence can remain integrated rather than dissolving into isolated parts. Leaving the Milky Way is not just a technological milestone, it is a transition into a fundamentally different mode of existence where unity is no longer guaranteed. Every law we have discovered, relativity, thermodynamics, quantum mechanics, seems to enforce locality. The universe may be fundamentally built to prevent instantaneous global coordination, limiting how far coherence can extend. Intelligence is not just about scale, it is a highly coherent system of interacting parts. Gaining cosmic reach comes at the absolute cost of identity. At the deepest level, the question of leaving the Milky Way is not about physics at all. It is about whether intelligence is meant to remain unified or become distributed. And the universe itself seems to suggest that unification has a natural limit, beyond which fragmentation is inevitable, not as a failure, but as a consequence of reality itself. So when we imagine humanity 1 million years from now, spreading across galaxies, we are imagining something that may not actually preserve what we intuitively mean by humanity. We are imagining copies, branches, divergences, and isolated evolutions of intelligence that no longer share a common present or perspective. And perhaps that is the real hidden truth behind the idea of intergalactic civilization. It is not a story of expansion, it is a story of transformation, a transition from unified existence into distributed existence, from coherence into dispersion, from a shared reality into isolated realities that can no longer fully overlap. Which brings us to the final question. If leaving the Milky Way requires sacrificing coherence itself, then what exactly are we trying to preserve when we imagine doing it? Because perhaps the universe is not asking whether we can leave. Perhaps it is asking whether what leaves would still be us at all. If every layer of physics, cosmology, identity, and causality converges toward the same conclusion, then the final step is to return to the beginning. Not the beginning of the universe, but the beginning of the question itself. This is why we will never leave the Milky Way. At first, that statement sounds like a limitation of technology, a barrier waiting to be solved, a challenge for future engineering. But as we move through the layers of reality, speed, energy, space-time, information, identity, expansion, and coherence, it slowly transforms into something much deeper. It stops being a technological problem and becomes a structural property of the universe. What we have discovered, step by step, is not a single wall blocking intergalactic travel, but a layered architecture of constraints that all point in the exact same direction. Distance is too large, speed is fundamentally limited, energy requirements explode exponentially. Spacetime resists manipulation at scale. Information remains bound by causality. Identity fractures under copying and delay. Cosmic expansion isolates regions permanently, and coherence itself breaks apart as scale increases. Each layer alone might seem solvable, but together they form something else entirely, not an obstacle, but a boundary condition of existence. Once we recognize that pattern, the meaning of the Milky Way fundamentally changes. It is no longer just a galaxy. It becomes a region of coherence, a volume of spacetime where causality still allows shared interaction, synchronized experience, and unified intelligence. It is the largest known structure where we still functions as a meaningful concept. Beyond it, that concept begins to dissolve. Not instantly, not violently, but gradually, like ink spreading in water. Step back and consider what this implies about every dream of cosmic expansion. We often imagine the future as a straight line of progress, more technology, more reach, more control over the universe. But physics suggests a much more complex picture. Progress increases capability, but capability does not remove structural limits, it only pushes against them. And the further you push, the more those limits reshape what progress even means. At small scales, civilization is defined by movement. We travel, we build, we expand geographically. At planetary scales, civilization becomes defined by systems, energy networks, communication infrastructure, global coordination. At stellar scales, it becomes defined by resource control, harnessing the output of stars and engineering on astrophysical levels. But at galactic scales, something subtle happens. Coordination begins to fail. Not because intelligence decreases, but because time delays increase beyond usable thresholds. At that point, civilization stops being a single actor. It becomes a distributed pattern of related systems. And beyond that, at intergalactic scales, even that pattern dissolves, leaving only isolated islands of intelligence, each evolving independently. So the question is not whether expansion is possible. It clearly is, within limits. The question is what remains of unity after expansion, and physics suggests that unity has a maximum scale. Not because it is forbidden, but because causality is finite. Information cannot propagate infinitely fast. Interactions weaken with distance, and time itself stretches across space in ways that prevent global synchronization. Even if we imagine a civilization capable of reaching other galaxies, we must confront a difficult truth. It would not remain a single civilization in any meaningful sense. It would become something else, a family of divergent histories sharing a common origin, but no shared present. Consider what this means for humanity specifically. When we imagine future humans spreading across the universe, we tend to imagine continuity. We imagine us expanding outward, colonies that still feel connected, coordinated, and part of a shared identity. But that assumption depends on something physics does not guarantee: that communication remains fast enough to preserve unity. Once that breaks, everything else follows, because identity is not just memory, it is interaction. Without interaction, shared identity becomes symbolic rather than real, a label applied to systems that no longer influence each other in meaningful timeframes. So when we say humanity will reach other galaxies, we must ask a more precise question. Will anything that reaches them still be meaningfully human in the sense we understand? Or will it be a descendant pattern, diverged so far that the original meaning is lost? This is where the idea of intergalactic travel begins to blur into something more philosophical than physical. Travel implies continuity. A traveler leaves one place and arrives in another as the same entity. But across cosmic distances, continuity breaks down. Time dilation, communication delay, cosmic expansion, information loss, all of these erode the thread that connects origin to destination, until arrival becomes indistinguishable from transformation. Return to the Milky Way itself. From within, it appears ordinary, just a spiral galaxy among billions. But from the perspective of coherence, it is something exceedingly rare. It is a stable, causally connected structure in an increasingly disconnected universe. It is large enough to contain complexity beyond imagination, yet still small enough to allow interaction across its full span within cosmic timescales. That combination is not guaranteed everywhere. In fact, it may be extremely rare in the long-term evolution of the universe, because as expansion accelerates, more and more regions fall beyond causal reach. The universe does not remain uniformly connected, it fragments, which means the Milky Way is not just a home. It is a window of opportunity, a temporary region where unified civilization is still physically meaningful, and that window may not remain open forever. Instead of asking why we cannot leave the Milky Way, we might ask why we are here at all in this particular era of cosmic history. Cosmic expansion is not static, it changes over time. There are epochs in which galaxies are more connected, and epochs in which they become isolated. We appear to exist in a transitional era, where local structures are still coherent, but large-scale structures are already drifting apart. This is a rare moment in the universe's timeline, a moment where expansion is visible, but not yet fully isolating local systems from each other. Which introduces a profound idea. Maybe the real limitation is not space. Maybe it is timing. Civilizations may not be blocked from intergalactic travel in principle. They may simply exist in eras where such travel cannot preserve meaning. Even if a journey is physically possible, it may arrive too late to connect with anything that remains stable. Look at the full picture. We began with the dream of becoming a cosmic civilization, imagining humanity spreading across stars, then galaxies, then beyond. But every step into larger scales introduced new forms of fragmentation, not just technical fragmentation, but structural fragmentation. Distance fragments communication, time fragments coordination, relativity fragments simultaneity, expansion fragments reachability, information fragments identity across delays, and coherence fragments at large scales. The deeper pattern is not expansion, it is decomposition. A gradual transition from unity to multiplicity, from a single coherent system to a distributed family of systems that share origin but not experience. And if that is true, then the Milky Way is not a prison in the sense of confinement. It is a boundary of unity, a region beyond which we becomes them, not because intelligence disappears, but because connection dissolves. Here is the final inversion of the idea. If leaving the Milky Way means losing unity, then perhaps the true goal was never to leave at all. Perhaps the goal is to understand the structure we are already inside, to recognize that coherence itself is the rare resource. Not energy, not matter, not space, but the ability for systems to remain meaningfully connected across distance and time. And if that is the most fragile resource in the universe, then the Milky Way is not something to escape. It is something to understand deeply while we still can, because beyond it lies not emptiness, but separation, not silence, but disconnected voices that can never fully synchronize again. That changes the emotional core of this entire journey. It means that the universe is not denying us access to greatness. It is defining the scale at which greatness can remain unified. When we look at the night sky and imagine intergalactic futures, we are not wrong to dream, but we may be misunderstanding the nature of what those dreams become. They do not end in a single expanding civilization. They end in a scattering, a diffusion of intelligence across regions that no longer share a common present. In that sense, the Milky Way is not the edge of human ambition. It is the edge of shared reality. The final region where a civilization can still say we and mean something physically precise. Beyond it, we becomes a memory, a label, a story told across delays too vast to ever reconcile. And that is the final realization hidden inside the idea that we will never leave the Milky Way. Not that we are trapped, but that unity has a horizon, and we are already standing inside it, looking outward.